We'll proceed in vector summation and integral calculus. Okay, so we are proceeding in vector summation and integral calculus. And there mainly we are concerned about the Taylor series. The Taylor series is the series which does the approximation of any algebraic equation into set of set of polynomial equation. This is what the Taylor series is. Can we approximate a algebraic equation in terms of can we can we approximate an any algebraic equation in terms of set of polynomial? What is set of polynomial is a0 x to the power 0 plus a1 x to the power 1 plus a2 x square plus a3 x to the power 3 a4 x to the power 4 a5 x to the power 5 a6 x to the power 6 and so on. This is typically called Maclaurin series, which is a corner case of a Taylor series. So Taylor series is saying that we can talk about function which is at any position. Maclaurin series is saying a function which has intersection with the origin. Okay. Okay. So this is a function. This is a circle, and it is a function. Circle is a function means y equal to square root of a square minus x square is the equation of the circle. Y equal to square root of a square minus x square. Fx equal to square root of a square minus x square is the equation of the circle. Y is nothing but fx. Fx means height. Fx means height. Means if this is the circle, if this is the circle, if this is the circle is centered at the origin. The equation of circle fx equal to square root of a square minus x square. This equation can be described as a0 into x to the power 0 plus a1 into x to the power 1 plus a2 into x to the power 2 plus a3 into x to the power 4 plus a and x to the power 1. This is what it is. Mr. Taylor is saying that what if the function what we are taking like a circle what we are taking circle is not centered at the origin. Okay, this is the equation of circle, that is x square plus y square equal to a square. X square plus y square equal to a square, because circle is centered at the origin. What about circle is not centered at the origin? Circle is centered at any point A. Circle is shifted now. This is what he is saying. What about if circle is shifted? If circle is shifted, then now it is centered at point A from X. Okay, then it will be, in that case, the equation of circle will be y equal to the square root of a square minus, and instead of x, it will be x minus a and bracket whole square. If it is shifting by a, so now it is complete, because circle can be at any location, not required it is at center only. This is what Mr. Taylor is saying, that it is not required that circle will be always centered at the origin. It can be at any location A from X. A from X. Okay, this is what he is saying. Someone would say that what about it has interception along the it has interception along the y-axis. In that fashion, equivalently, it can be made interception along x-axis. Someone can try for the circle. I can tell for the line. If this is origin, if this is the origin, and there is a line that is passing the origin, there is a line that is passing the origin. If I say x minus a, this line is passing at x equal to a. Okay, this is A. If this is y-axis and line is passing point B along y-axis, then if I draw a straight line, then it will pass at A along x-axis only. So just with the x-axis, cutting at the x-axis, actually we can demonstrate the equation of the any curve or line. So Mr. Taylor is saying that fx equal to a0 x minus a to the power 0, where the fx is shifted at a. Makes sense? If I have any fx, if I have this is fx, I have any fx which may not be centered at the origin always. No guarantee that it is centered at the origin always. In that case, wherever it is centered, that is a distance from the x. Now, wherever it is centered here, we can bring in a term of a, that is displacement from x. In that fashion, fx equal to a0 into x minus a to the power 0 plus a1 into x minus a to the power 1 plus a2 into x minus a to the power 2 plus a3 into x minus a to the power 3 plus an x minus a to the power n, where x minus a is shifted. If I have a shifted circle that is shifted along x-axis and centered at a now, then it will be x minus a whole square plus y square equal to a square. Or if a is the radius and it is shifted any amount alpha, then it will be x minus alpha whole square plus y whole square equal to a square, where circle with radius a is shifted alpha along the x-axis. Okay, that is the scenario. That is the scenario called shifted. So Taylor series talks about the shifted. Okay, how much something is shifted, the equation should be in terms of shifted one. So fx equal to a0 x minus a, because x is the equation is shifted to a, shifted a. So a0 into x minus a to the power 0, 0 plus a1 x minus a to the power 1 plus plus. This is what Taylor is saying. Mr. McLaurin is saying that it is same as considered, rather than going for a very natural position of any curve. Like if I have a sinusoidal curve, if I have a sinusoidal curve, this is a sinusoidal curve. This is a sinusoidal curve. If this is a sinusoidal curve, this is origin. Okay, Taylor is saying the sinusoidal curve may start from the A, not from the origin, because this is natural tendency that it may not start from the origin itself. McLaurin is saying consider A is 0. Take the normal case A is 0, because it doesn't look elegant that any fx equal to a0 into x minus a to the power. Everywhere x minus a is there. That does not look elegant. So fx equal to a0 plus a1 into x plus a2 into x square plus a3 into x to the power 3 plus 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 plus. This is what Mr. McLaurin is saying. Okay, we respect both of them and both are equally precious. Okay, now we are the way Mr. Taylor has proved the any function can be described. Any function fx can be written as set of polynomial equation a0 x minus a to the power 0 plus a1 into x minus a to the power 1 plus a2 into x minus a to the power 2 plus plus. Anyone would say that I understand that any function can be written as a polynomial equation. I understand. What is a0, a1, a2, a3? If you find that, then I will be happy in that. Then Mr. Taylor is saying, do one thing. You take the value of fx at x equal to a. If you do like so, consider fx equal to a0 into x minus a to the power 0 plus a1 into x minus a to the power 1 plus a2 into x minus a to the power 2. Consider this is the fx. Fx is represented like this. What is the value of fx with x equal to 0, x equal to a? All become 0, only a1 will a0 will remain. So a0 is fx when x equal to a. I can strike out a0 and place there fx at x equal to a. Now go again fx equal to whatever we have written. Take single derivative of fx and calculate single derivative of fx at x equal to a. Then this side a0 term will go away with the first derivative. Only a1 will remain, otherwise will become 0 when x equal to a. If that is the case, then a1 equal to derivative of fx at x equal to a. Now a1 what we had written, I strike it out, and there I place single derivative of fx at x equal to a into x minus a. Now, Mr. Taylor is saying do dual differentiation. If I do dual differentiation of fx, then first two term will go away. Then it will be 2a2, 2a2. That's it. 2 into a2, or rather I would say 1 into 2 into a2, 2 factorial into a2. Okay, plus every term will be in x minus a. Now double differentiation when x equal to a, then everything will become 0. 2 factorial into a2 will remain. So a2 will be double differentiation of fx at x equal to a by factorial of 2. Now I can strike out a2 and place their double differentiation of fx divided by factorial of 2, and then x minus a whole square. Similarly, triple differentiation of fx at x equal to a divided by factorial of 3 x minus a to the power 3. This is the Taylor series. Mr. McLaurin is saying, Sir McLaurin, he is saying that don't why you are doing this much. Just say a equal to 0. Let if you have a sinusoidal wave, if you have a sinusoidal wave which starts at any point x equal to a, this is the origin. If this is the origin, then it is starting from any point x equal to a. Then it start at x equal to 0. What is the problem? There is no problem. Then everything will be same. Now it is nicely written as fx equal to f0, f0, okay, plus derivative of fx at x equal to 0 into x plus derivative of fx at x equal to 0 by factorial of 2 into x square. Now we are saying that we will proceed with the another proof, and this proof is more concrete than what Mr. Taylor has said. Actually, I invented this. I have already said this. I invented this with other mean also, not this mean. Then I found that it is already done by Sir Taylor. Okay, because this makes any problem drastically simple. I have already said that Euler, Mr. Euler, who happened to be a very famous mathematician, and he brought that e to the power I theta exponential to the power I theta equal to cos theta plus I sin theta. Whenever I was studying this, that e to the power I theta equal to cos theta plus I sin theta, this is the Euler's formula. I used to think that God has given separate brain to Mr. Euler. Because in dream also no one can write like this, e to the power I theta equal to cos theta plus I sin theta. It is impossible. Then I saw that Mr. Euler is a very high concentration person. Means he concentrate anything to any extent. Then he wrote the Taylor expansion of e to the power I theta, or Maclaurin expansion of e to the power I theta, and he wrote it. Then he wrote the Taylor expansion of cos theta. Then he wrote Taylor expansion of sin theta. Then he saw the Taylor expansion of I theta is nothing but a mixture of cos theta and I sin theta. Exactly like that. And then he said it is in this fashion. Okay. And that became another pillar stone in the arena of mathematics, big invention that we will see. We will have real hardware where we will have LCR circuit with a battery, and we will show it is oscillating, and then where Mr. Euler or Sir Euler's formula will come into the picture, where it will start resonating, means it will start oscillating. So that we will see. Anyway, now we have our own proof that Taylor series is actually nothing but calculation of the area by dividing the area into n different parts. This is what we are talking. Okay, if I'm talking like that fashion, then consider there is a curve like this that is similar to 1 by x. There we started. Or I can take a curve like this also. It is up to me. I can take a curve like this also. Okay, I believe it is all right. Or if I take a curve like this, I take a curve like this, or I take a curve like this, I take a curve like this. Make sense? I take a curve like this. If I take a curve like this is 1 by x. This is 1 by x. Where at x equal to 0, it has I always misspell this. Asymptotic asymptotic. Asymptotic means it is touching the y-axis, but it is not exactly the y-axis. So this asymptotic. Okay. So asymptotic at the x equal to 0 means if I have 1 by x when x equal to 0, then it will go to infinity. Otherwise, it will tend to 0. Similar function I'll take, but it is not going to infinity. It will touch x-axis, y-axis like this, and it will flow along the x-axis like this. Or someone can take like this also. There is no problem in that. Okay. Now concept is if I take like this, consider this is 0 and this is x some point. This is 0 and this is x some point. And then I am saying what is the area of this curve? What is the curve? Fx, function over x. A function over x can be cos x. The way it looks like, it really looks like cos x. Can someone see? It really looks like cos x. So the function is fx. What is the area of this between 0 and x? Anyone would say immediately fx dx. What is the area of this? I'm asking another guy. Okay, do you know integration? No, I don't know integration. What is the area of this? Area of this looks like this is a flat line. I have demonstrated this in past session also. Looks like this is a flat line. Looks like this is a flat line. If it is a flat line, then this is x, 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 and flat line. If I multiply height by width, this will give the area. What is the height of this flat line? Whatever the value of fx at x equal to 0, if this is x equal to 0, what is the value of fx at x equal to 0? In that fashion, this is the value of fx at x equal to 0. Make a flat line, then I can say f0 or fx at x equal to 0, that is the beginning height, multiplied by x is the area. Okay, then someone said, just go and see your with binocular that what you have done. You took this as a, yeah, it is a straight line. See, it is a straight line. Okay, after that, it is making a curve. It is not a full straight line. I'm sorry. Then what I have to do? I calculated this as a area as a straight line. Then by mistake, you calculated area up to here. If this is x, if this is x, and this is y0 fx at x equal to 0, 0, then you calculated this full area. You have to subtract this region, boss. Then only you will get the actual area. Now another one is saying, okay, probably you have to subtract that area that you calculated in kind of in more way, in advanced way. So what area you calculated is this height by this width, that is x. So height full rectangle you calculated as fx at x equal to 0 into x. Now what I need to subtract, someone would ask. Now for if this if consider this is x for simplicity. What you have to do now? Take a straight line from here and connect a straight line here and calculate the area that you have to subtract now, because that is the error. What is the error? This line and this line. This triangle is the error. Oh, understood. Okay, actually I forgot. This is not a straight line, flat line. This is a slant line. See, now that person is somehow he started seeing it as a slant line. First he was seeing it is a flat line and he said area is f0 into x. Now suddenly he started seeing it as a slant line. When it is a slant line, then what is the area of this triangle, top the triangle? Then area of this triangle is x into y by 1 by 2. That is the area of any right angle triangle. It makes right angle here. Right angle triangle area is both side multiplication by 1 by 2 into 1 by 2. What is y? Okay, then he is saying what is y? Y is the what is y? Okay, if I know this line, if I know this line dy by dx, if you give me dy by dx or y by x, what is y by x? If this angle is theta, if this is a straight line and this angle is theta, tan theta I want. Tan theta is y by x. If you give me tan theta of this angle, that is y by x, if I multiply y by x with this x, it will give me the height into x. Means 1 by 2 into y by x into x. Y by x into x will give the height into x, that is the width. Y by x, now I say I don't know what is y by x, because it doesn't look like a straight line. He will say, but it looks like, let's take derivative. Let's take derivative. Y by x, make it dy by dx. Dy by dx at what point? Everywhere dy by if I take this as a curve, everywhere dy by dx is different. Dy by dx is the slope, that is tan theta, that is different. Take dy by dx at origin only. Okay, if you take dy by dx as origin, then it will go like this. Make sense? It go like this. Then dy by dx into x will give the height into base x 1 by 2. 1 by 2 dy by dx into x. That will be the area of the triangle. Then now it is complete. What is the area here? Now if someone is watching it, we are dividing the calculation of area into two parts. Now, one part is rectangular part and another part is a triangle part. More or less, I would say, if this is the curve, more or less we have divided this into two parts. One part is a rectangle part and another part is the triangle part that we are seeing like this. This is the triangular part. This is the triangular part. From rectangle, I subtracted the triangular part. Okay, now anyone would say, but rather than subtracting along this curve, and this area, you subtracted the dy by dx at x equal to 0. At x equal to 0, dy by dx is like this, and it will go and it will hit this line at here. This portion you missed was, okay, see, this line will go and it will hit this line at this point. Then the triangle you took is here. This portion you missed. Oh, I missed this portion. Yeah, you missed that portion. That portion is required. So rectangle minus the triangle and minus this portion. What is missing now? If this is the curve, then first you calculated the rectangle region. Then we saw that you calculated extra. Whatever this above this line is extra area. We want the area underneath this line, not above the line, but you calculated this region extra. When you are taking dy by dx at x equal to 0, then line dy by dx line goes like this. Then this triangle you subtracted. What about subtracting this triangle? This triangle you have to subtract. This area you have to subtract. Now he will say, I am done with the flat line. I am done with the curve line. Okay, what else is remaining now? Then what else is remaining now? The another line, that is x square. What I'm trying to say is, first line is y equal to 0. That is the flat line through which someone calculated the rectangle. First line is a flat line through which someone calculated the rectangle. Second line is a slant line, that is dy by dx. Dy by dx, if I calculate dy by dx, it will give the equation of a slant line, means slant straight line. Then I calculated the area of the triangle. What is remaining? Now this part is remaining. If this part is remaining, then I have to think, that looks like what mistake you did. Someone would ask, what mistake you did? Actually, I was thinking it is a flat line. If it is a flat line, then I calculated the area of it, thinking rectangle. Then I saw, rather than a flat line, it is exactly a slant line. Then I calculated the triangle area. Then I am saying, if it is not a slant line, then what else? Then next degree. Then you have to think next degree. First degree is x to the power 0, y equal to x to some constant x to the power 0. That is the equation of flat line. Next is y equal to some constant into x. That is the equation of slant line. Okay, but there is no slant line. I am getting slant line through the first derivative. That is the difference here. Rather than directly going with 1 by 2 y into x, people would go 1 by 2 into y into x, or 1 by 2 x square, something like that. But this is not 1 by 2 x square or 1 by 2 some constant x square, because dy by dx we are calculating as a line equation. Then what mistake you did? First I thought it is a flat line. Then I thought it is a slant line connecting begin and x point. Slant line connecting. Then I thought, someone would say, then I thought This is exactly a slant line, exactly a slant line. Okay, to have the slant line equation, I took derivative at x equal to 0, but unfortunately, it came like this. So this area is still remaining to subtract from the first rectangle. Okay, what is this area? I'm sorry, I took a straight slant line. Actually, it is x square. First was x equal to 0. First was x to the power 0, then slant line means x to the power 1, and then now I am taking x square inter, means I have to calculate dual derivative. I have to calculate. I have now I am seeing the person is seeing this line as a y equal to x square. Earlier he was seeing line as a y equal to x, means a slant line. First he was seeing y equal to constant. Then he started seeing as y equal to x. Then he started seeing y equal to x square. So that he is trying to calculate the remaining area. Y equal to x square, something like that. Okay, then what will be the remaining area when y equal to x square? If someone reads in the book similar thing, I'm not saying that the Taylor series, similar thing, then he will find that area will be third area will be x to the power 3 by 3. Third area will be x to the power 3 by 3. The way the second area is x square by 2. I mean dy by dx, by dx at x equal to 0 into x square by 2. That is the triangular area or second area. First area is rectangle. Third area will be d2 fx by dx square into x to the power 3 by 3. This is what is written in one of the best book I have seen in calculus. That is completely wrong. This is what I am trying to say. Completely wrong. What we are trying now? We are trying to calculate area. We are trying to calculate area through the dual derivative now. Through the dual derivative. I don't have any equation like y equal to x square. I am imagining. But I am going with the dual derivative now. That is the concept we are following. Okay, let's see what is the dual derivative of x. If I say dual derivative of anything, consider I have a polynomial, and that is x to the power 3. What is dual derivative of x to the power 3? Then it will be 3 into 2 into x. What is dual derivative of x square? It will be 2 into 1. What is dual derivative of x to the power 4? Then it will be 4 into 3 and then 4 into 3x square. This looks like that after doing dual derivative of something, we are getting two coefficients, not one coefficient. That is the biggest thing. Anyway, what is differentiation and what is integration? What is similarity between, what is the relationship between integration and differentiation? If I say I have a function x to the power n, then integration will be x to the power n plus 1 by n plus 1. Means I have to, if I am integrating fx dx, then it becomes gx. If I am integrating fx dx, then it becomes gx. Okay, what is differentiation? If I talk about differentiation, integration is nothing but reverse of differentiation. Fx into dx equal to gx. If I take dx down, it will become dgx by dx equal to fx back. If I want fx back from a result called gx, then I have to differentiate it. If I differentiate it, I'll get fx back, for which integration is gx. That is relationship. Anti-integral is derivative. I'm sorry. If integral of something, if integral of fx is gx, then derivative of gx is fx back. Derivative of gx is fx back. Okay, someone can interpret antiderivative and anti-integral here, but this is how it is. Now, if I'm talking that if I'm talking about the third region, first region is rectangle, second region is triangle. If I'm talking about third region, then there the equation of a line is in such a way that if I do dual derivative, then it will become a flat line. Like if I have a slant line and if I take single derivative of a slant line, then it will become a constant. Makes sense? What is equation of a slant line? Y equal to mx, where m is a constant. If I take single derivative of a slant line, then dy by dx will become a constant. Constant means a flat line, and then I can calculate the area of it as good as a rectangular area. If I am going with the dual derivative, then expectation is after dual derivative, it will become a flat line. If expectation of a slant line that I took as a triangle, expectation of a slant line is if I take single derivative, it will become a rectangle. Then expectation of the next line that I am taking as a x square. First I took as y equal to some constant into x. Now I am taking the next line as y equal to some constant into x square. Because I am thinking there I am missing. That's why some area remained. I should have taken x square also into the consideration. This is what my thinking is. This means that if I take if I calculate dual derivative of this line, then this dual derivative will result into a constant, and that will be if I multiply that constant with the width, constant means height, equal height, that is constant. Y equal to constant means equal height. Then I can calculate the rectangle anyway. Now, what is the similarity between calculating area, calculating area, and then what calculation of the area result is calculation of fx dx, that is calculation of area under fx results in gx, that is the another function that is actually area. Fx dx equal to gx. Gx is nothing but a function with area. Keep changing x, you will keep getting different area. Gx represent area, whereas fx represent a curve line. Okay, that is the difference. But the relationship between them is if gx is x square, if gx is x square, if I take dual derivative, then it will be 2 into 1 will come out. If it is x to the power 3, if I take dual derivative, then 3 into 2 will come out. If it is x to the power n, if I take dual derivative, then n into n minus 1 will come out. If that is the case, then what is antiderivative in relationship with integration? This proves that if I do integration, if I am involved in doing integration of something that has dual derivative, then since integration is opposite to derivative, two things will come down. Makes sense? If I take dual derivative, the two coefficients are coming out from the x in polynomial case. If it is x to the power n, and if I take dual derivative, then two coefficients are coming out, n and n minus 1. Then x to the power whatever it is. If integration is anti of derivative, then equivalent integration will show that two coefficients will come as denominator. Makes sense? Like n into n minus 1 at denominator, whereas differentiation, two coefficients will come out as numerator. If I take triple differentiation, then three coefficients will come out as numerator. If I take opposite to it, antiderivative or something like that, then three coefficients will come below it as denominator. One side is numerator, one side is denominator. Anyway, now we are trying to find the area. We are trying to find the area of the third shape where dual derivative is involved now. When dual derivative is involved now, if dual derivative is involved now, and then we are trying to calculate area. Area means integration. Area means integration. This proves that equivalent of dual derivative in integration will be two coefficients will come in the denominator. This is what I am saying. Okay, if that is the case, then what will happen? Dfx by d2fx by dx square will be a constant. Means I have to differentiate till it reaches the constant. Okay, d2fx by dx square. Okay, first, if I differentiate in one go, like if I have seen that if when we were trying to calculate the area of the triangle, then I differentiated it one go and then multiplied with the x and divided by 2. Similarly, here if I differentiate it first time, the first time, then probably I think so. It will be dfx by dx into x by 2, something like that. If I differentiate next time, then it will be d2 fx by dx into x in bracket into x, one more x will come, by 2 is already there, into 3. Okay, so this will be the term, that will be a term that will become vertical side if I calculate the area of rectangle. Means if I do double differentiation, then it will come as a constant that I can multiply with the x to have an area. So it will become like dfx by dx. Someone can think in other way also. Okay, more research is required here. Dfx by dx into x by 2. This is the component that is equivalent to more or less for the first differentiation. Then we will go for second differentiation of this item 1. Then it will come as d2, considering x is constant, d2 fx by dx square into x. That is the first one. And then multiply by x again, divided by 3, whatever was there. So it will become d2 fx by dx square into x square divided by 2 into 3. Okay, double differentiation means two numerator will come as from the polynomial. If I do double differentiation of any polynomial, two numerator will come out. First differentiation, one numerator. Second differentiation, one more numerator. Here also, when we are trying to calculate in the arena of area, then two denominator will come out, because it is opposite to differentiation, integration factor, whatever. This is one technology. Another technology is someone can go layer by layer, the way we have discussed in the past video. Layer by layer. Means first layer is where the height is constant, that is rectangle. Second layer is where height is a slant line, that is first derivative layer. Third layer, or zeroth layer, first layer, second layer. Second layer, where the first derivative will be a slant line, second derivative will be a flat line. First layer, first derivative will be a flat line, whereas normal is a slant line. Second layer, normal is x square. First derivative will be a slant line. Second derivative will be a flat line. So that I can calculate it in a rectangular manner. If I take first derivative, then it will be divided by 2. If I take second derivative, it will be divided by 3. Whatever. That's why I say someone can think in any manner. Okay, whatsoever, if I'm trying to calculate area of a rectangle where height and width, if I multiply, it is the area. If I do double differentiation of x square, it will result in constant only, and that is the height. And that height is coming as d2 fx by dx square into x square by 2 into 3, multiplied by the base. So the third reason I'm saying that is remaining. I'm sorry, I forgot to calculate it. The third reason what I am saying, and that is nothing but d2 fx by dx square into x to the power 3 by factorial of 3. Okay, then someone would say, boss, still something is missing. What I can say, unfortunately. First, you took this as a flat line. Yeah, it is a flat line, because when x equal to 0, I saw it is a flat line, but actually it turned after that. Then he said, oh, I'm seeing now I'm seeing it is a slant line. When he is thinking slant line and he took dy by dx at x equal to 0, then he landed up in a slant like line like this, and he left this region to be calculated. Then he did dy by dx two times at x equal to 0. Okay, first time a slant line, again dy by dx. Okay, then he tried to calculate the remaining area, what is not achieved in the triangular area, another area. Then someone is saying still something is missing down the line. Then I have to take triple differentiation at x equal to, then fourth differentiation, then fifth differentiation, sixth differentiation, till we complete the full area. Okay, how many time will take? N tends to infinity times I'll take. Okay, now I'm happy that area is calculated. What is your area, boss? Finally, you have to disclose what is your area. Area is area of this. If this is x-axis and this is y-axis, I'm taking 0 to x, where this is the any equation of any arbitrary curve fx is there. If I talk about the area is nothing but the area inside is between x equal to 0 to x. This area is nothing but fx dx. In general term, fx dx integration equal to f0 into x plus dfx by dx at x equal to 0 into x square by 2 plus, or in better term, if I say that it will be dfx by dx into x by 2 in bracket, again d of it into x by 3. It will come at d2 fx by dx square into x to the power 3 by factorial of 3, x square by factorial of 3 into x plus d3fx by dx cube into x to the power 3 by factorial of 4 into x. Like that, someone can continue. Okay, now differentiate both sides. If fx dx is the area, then if I differentiate, only fx will come out. Only fx will come out. If I differentiate, then all the term I have to differentiate. F0, first is f0 into x, it will become f0. Second is dfx by dx at x equal to 0, which is a constant, into x square by 2, it will become x, plus d2fx by dx square at x equal to 0, that is a constant, into x to the power 3 by factorial of 3, it will become x square by factorial of 2, plus d3fx by dx cube into x to the power 4 by factorial of 4. It will become 4x to the power 3 by factorial, x to the power 3 by factorial of 3. Like that, it will go on. It will become dnfx by dxn, at time differentiation, into x to the power n by factorial of n. This is extremely solid proof. This is extremely solid proof. I thought of proceeding into 3D also. What is 3D? Okay, 3D is consider this is xy plane. If this is xy plane, then if this is xy plane, then I have arbitrary shape like this. Okay, what do you want with the xy plane? I want Taylor series in multivariable case. What is multivariable case? So first we saw dividing area into n different parts and calculating the area by area and then sum it. Sum is negate, subtraction is summation only. Direction is opposite. That's it. Anyway, if I talk about what is fxy, fx equal to, I understood. What is fxy? Function over x and y. Can you divide into n different parts and tell me what it is? What is fxy? Fxy means it's an equation of a surface. If this is xy plane, then xy is the surface earlier independent component was x. Now independent component is xy plane. If I talk about this fxy, then it is a surface. If I take for any, if this is origin for any x and for any y, the way we did there took for any x. If I take a particular xy region and I take intersection here along, then this is a volume underneath. This is the volume underneath it. Okay, someone will say it is very simple. When consider this is going intersection at origin. At origin, what is fx0, fxy? Then that is fxy at x equal to 0, y equal to 0. And then multiply by x and multiply by y. That's it. That is the volume. What is the volume? Fxy dx dy. If someone know it, calculating the volume of fxy. Fxy dx dy integration is the volume, that is equal to fxy at x equal to 0, y equal to 0 into x into y, that is the volume. I know it, but that is not a flat surface. That is something like this. The way we started with the rectangle, no, it is a cuboid, but it is not a cuboid. The top surface what you are thinking above it is not the flat, it is little slant. Okay, oh sorry. Then I have to, I did not think it is extra, right? Yeah, it is extra. Up to here you calculated. 0. Up to here you calculated. This area you missed it. This volume you missed it. Okay, then someone has to calculate this volume. This is not a straight slant line. It is like this. Oh, that I missed. Keep calculating like this and finally you add, then differentiate it with the xy plane rather than differentiate with x. Earlier, we differentiate with xy plane. Then someone can try in the 3 dimension also, 4 dimension also. This is our proof. This is not available in any of the book, and this is I would say this is less confusing than what Mr. Taylor at the beginning only he took any fx as a series of polynomial equation and where he just idea was to find a1, a0, a1, a2, a3, a4. Those are the coefficients. Here from the scratch, we have started with a different approach at all. That is calculation of the fx with calculating the n, dividing our area or volume into n different sections and adding all of them and then differentiating it. This is mind blowing and this is head eating and this is completely different approach. We will publish it. Probably we will do more on it. Please do not mind supporting us. +91 is the India country code 9483160610 is the telephone number. +91 is the India country code 9483160610 is the telephone.